Hello everyone. Today we are going to discuss about dielectrics. Before that, let us know that physical materials are divided into three types based on the electrical conductivity, that is conductors, semiconductors and insulators. Conductors, the materials in which outer electrons of the atom are loosely bound to the nucleus and free to move through the material are known as conductors. Effect of temperature on conductors. If we increase temperature of conductors, then the resistance increases. Example, copper. Here in this picture, the electrons are free, thus it allows the current to pass freely. Semiconductors. The materials in which the outer electrons are slightly bound to the nucleus are known as semiconductors. Effect of temperature on semiconductors. If we increase the temperature, the electrons get free from nucleus and conductivity increases. Example, germanium, silicon, etc. Insulators. The materials in which outer electrons of the atom are tightly bound to the nucleus and there is no free electron for conduction are known as insulators. Effect of temperature on insulators. Though we increase the temperature, the resistance in the insulators remains constant. Example, dielectrics. Here in this picture, the electrons are not free, thus it does not allow the current to pass freely. Dielectrics. These are the contents to be discussed. Introduction to dielectrics. The term dielectric was named by William Weber from dielectric in response to a request from Michael Faraday. A perfect dielectric is a material with zero electrical conductivity, thus exhibiting only displacement current ID. Therefore, it stores and returns electrical energy. Definition of dielectrics. The materials which may be a polar or non-polar material having the insulating property are known as dielectrics. Capacitor is the example of dielectrics. As we are telling that dielectrics are the insulators, what is the difference between insulators and dielectrics? Dielectric materials are insulating materials used to store electrical energy. Specifically, dielectrics are the materials which can be polarized. Thus, all dielectrics are insulators, but all insulators are not dielectrics. Types of dielectrics are polar dielectrics and non-polar dielectrics. Polar dielectrics are those in which the possibility of coinciding of positive as well as negative charge at the center of the molecule is almost zero, that is, they do not coincide. Non-polar dielectrics are those in which the positive and negative charge coincide at the center of the molecule. In polar dielectrics, the individual polar molecules have dipole moment, but when considered in a group, the net dipole moment becomes zero due to random orientation. In non-polar dielectrics, the individual non-polar molecules do not have dipole moment. Example, ammonia, hydrochloric acid, etc. Example, methane, benzene. These are some of the applications of dielectrics. Basic terms and properties of dielectrics. Electric dipole. The separation between any two opposite electric charges of same magnitude by a suitable distance is known as an electric dipole. A permanent electric dipole is called an electret. This is an electric. If an electric dipole is placed in an uniform electric field, as it has two equal and opposite forces at the two ends of the dipole due to opposite charges, it will experience no net force, but in general it will experience a torque. Electric dipole moment. The product of the either of the charge on the dipole and the distance of separation of the charges is known as electric dipole moment. The direction of dipole moment is always from negative to positive charge. It is denoted by mu. Therefore, mu is equal to q into 2r, where q is the charge of the dipole and 2r is the distance of separation between the charges. Units coulomb meter or debye. 1 debye is equal to 3.33 into 10 power minus 30 coulomb meter. Dielectric strength. If an electric field is applied to the dielectric material, then the highest voltage up to which the dielectric material does not lose its insulating property is known as a dielectric strength. Dielectric breakdown. If an electric field is applied to the dielectric material, then the lowest voltage at which the dielectric material loses its insulating property is known as the dielectric breakdown. Electric flux. The electric field in a dielectric material is studied by drawing the electric lines of forces. The electric lines of forces are also known as the electric flux. It is denoted by phi. The direction of electric lines of force is always from positive charge to negative charge. The tangent drawn on the electric flux at any point gives the direction of electric field at that point. Polarization. The electric dipole moment per unit volume is known as polarization. Units coulomb per square meter. It is denoted by P. Therefore, P is equal to mu by V. Electric flux density. The electric flux passing through the unit area of cross section is known as the electric flux density. Unit coulomb per square meter. It is denoted by D. Therefore, D is equal to phi by A, where phi is the electric flux and A is the area of cross section. Gauss law. Gauss law states that the flux emitting from a surface is equal to the total charge enclosed in the surface. Therefore, D is equal to Q by A. The electric flux density is also given by the following expression. D is equal to epsilon naught E plus P, where P is the polarization, E is the electric field intensity, epsilon r is the dielectric constant, and epsilon naught is the permittivity of the free space. Dielectric constant. The ratio of the permittivity of the medium to the permittivity of the free space is known as a dielectric constant. It is denoted by epsilon r. Dielectric constant depends on the following. These are dielectric constant values of some materials. Glass has the highest value, that is 7.75, and air has the lowest value, that is 1. In the absence of electric field, the dipole molecules are arranged randomly, so the net dipole moment is 0. But in the presence of electric field, the dipole molecules align in the direction of electric field, thus the net dipole moment becomes enormous. Hence, the dielectric is polarized. The types of polarization are electronic polarization, ionic polarization, orientation polarization, and space charge polarization. Electronic polarization. When an electric field is applied to an atom, positively charged nucleus displaces in the direction of field and electron moves in the opposite direction. This kind of displacement will produce a dipole within the atom itself, and whole atom will be polarized. The induced dipole moment is given by mu is equal to alpha E into E, where alpha E is called electronic polarization constant. Electronic polarization constant. It increases with increase in volume of the atom. These are the electronic polarization constant values for zero group elements. The Coulomb force experienced by positively charged nucleus and electron and the force due to electric field is given by Fc. The Lorentz force is given by Fl. The expression for electronic polarization constant alpha E is equal to 4 pi epsilon naught r cube. In the absence of electric field, there is no dipole moment. In the presence of electric field, the dipole moment is induced. Ionic polarization. The ionic polarization occurs when atoms form molecules, and it is mainly due to a relative displacement of the atomic components of the molecule in the presence of an electric field. The resultant dipole moment is given by mu is equal to q of h1 plus h2. When an electric field is applied to the molecule, the cations displaced by h1 to the negative side of the electric field and anions displaced by h2 to the positive side of the electric field. Ionic polarizability. It depends upon the mass of the ion and natural frequency and is given by alpha ionic equal to mu ionic by E. Orientation polarization. The polarization of polar dielectric is known as the orientation polarization. If the electric field is applied, then the dipoles orient in the direction of field and the dipole moment becomes enormous and the dipole is polarized. In the absence of electric field, the dipole molecules are arranged randomly, so the net dipole moment is 0. But in the presence of electric field, the dipole molecules align in the direction of electric field, thus the net dipole moment becomes enormous. Orientation polarization occurs at a frequency 10 power 6 Hz to 10 power 10 Hz. It is slow process compared to ionic polarization. It is greatly depends on temperature. The expression for orientation polarization is given by P naught is equal to N alpha naught E, where alpha naught equal to mu square by 3 kT. Space charge polarization. In a dielectric, in the absence of the electric field, the negative and positive charges are not separated. The induced polarization produced by the separation of positive and negative charges due to the application of the electric field is known as space charge polarization. In the first dielectric, as there is no electric field, the positive and negative charges are not separated. In the second dielectric, due to the application of electric field, the positive and negative charges are separated. This is the graph between polarization and frequency. Expression for polarization. P is equal to epsilon naught psi E, where epsilon naught is the permittivity of the free space, psi is the dielectric susceptibility, and E is the electric field. Dielectric susceptibility. The dielectric susceptibility is defined as 1 by epsilon naught E times of the polarization. It has no units. It is a measure of the extent up to which a material can be polarized by the application of the electric field. It is denoted by psi. Electric field strength. The force experienced by the unit positive charge placed in the electric field is known as the electric field strength. Units: volt per meter. It is denoted by E. Therefore, E is equal to F by Q. It is also called electric field intensity or electric field. Thank you.